So here's another related rates problem. In this case, you are videotaping a race car from a stand 132 feet from the track. Here's you. You're up here videotaping. Okay, you're videotaping a race car from a stand 132 feet from the track, following a car that is moving at 180 miles per hour, which turns out is 264 feet per second right here. How fast will your camera angle theta be changing when the car is right in front of you a half second later? So first of all, when you read this question, you realize they really snuck in an extra problem on you. They're first asking how fast your camera angle theta will be changing when the car is right in front of you. That's really like question A. And then a half a second later, that's question B. There's two different situations. And truthfully, none of those situations exactly is represented by this picture, right? By the time the car is right in front of you, it's actually right here. All right, and so that's designated by the fact this car is moving to the right, at 180 miles an hour. So it's going fast. It's going zoom that way, okay? As it's moving toward it, though, this distance is changing, right? It's getting smaller. So remember, we like to put variables on our pictures where measurements are changing. So this distance is changing, and so is theta. As the story indicated, it's getting smaller. And then in part A, we're asked how fast theta is changing. So what they're really asking is for us to find theta prime. Okay? The car is moving. This distance down here at the bottom is getting smaller, and so is theta. The car is moving to the right, and we are asked to find theta prime. So, first of all, based on this picture, I think you'll agree that we do have a trigonometric relationship. If we take a look at the tangent ratio of theta, that's going to be equal to x over 132. It's the old opposite over adjacent, opposite over adjacent. So this equation relates our two measurements. And what we'll be doing is we'll be taking the derivative of this equation and then plugging in the values that we know. Keep in mind that we're looking for theta prime, as I mentioned earlier, so we don't know that measurement. But we will know that theta is 0 when the car is right in front of us, when it's located right here, and so is x. We'll know those measurements, so that's kind of important. Now this slide is getting pretty messy, so I'm going to switch over to a blank one. We will rewrite what we know, and we'll take the derivative. Okay, so I've rewritten our information. Tangent theta equals x over 32 was the equation that we decided upon. We're trying to figure out what theta prime is. And at that moment, we know theta will be 0 and x will be 0. Now let's take the derivative. We do that derivative implicitly. So we're going to take the derivative of tangent theta with respect to time, and that'll give us a derivative of secant squared theta times theta prime. I'm going to write it out here just so it's clear that I'm multiplying theta prime by secant squared of theta. The derivative of x over 132 is 1 over 132 times x prime, so that's going to be x prime over 132. Now at this point we can plug some values in. I'm going to plug in 0 for theta, and although I haven't written it, I think we better indicate how fast that car is going. It said it was going 264 feet per second, but that x is shrinking, so that's really negative 264 in this case. Okay. So when we plug in all these values, we have theta prime, which is the value that the variable that we're trying to solve for. We're going to multiply by secant squared of 0. Well, cosine of 0 is 1, so is secant. 1 squared is 1, so this is just 1 squared, or 1. And then over here we're going to put in negative 264 over 132. And when we solve this, we get theta prime equals, what is this, negative 2, and that's radians per second. Okay. So for part A, when the car is directly in front of us, the angle is changing at negative 2 radians per second. Believe it or not, this is an R here. Now, part B is asking what that rate is a half a second later. And for that, we need a new picture. So remember, in our picture, you were up here on the stand. This was 132 feet. The car has now passed you by. It was directly in front of you, and a half a second later now it's moved this way. Here's the car. I'll draw an awesome rendering of that car here. And remember, it's going zoom that way, okay? So the question is, a half a second later, how far has it gone? Well, if it's traveling 264 feet per second, it means in 1 second it travels 264 feet. That means after a half a second, it has traveled 132 feet. And I think you'll agree that basically what we have here is an isosceles triangle, right? Here's our angle theta, the angle that the car is making with the line of sight of the camera. And if this is 132 feet by 132 feet, this must be a 45-45 right triangle, meaning that at this point theta is pi over 4. We know x is 132 at this point, and we know that x is growing, meaning that x prime is now positive 264 feet per second. And what we're going to do is we're going to go back to the same derivative we had before. It was theta prime times secant squared theta equals x prime over 132. We'll plug in all these new numbers. We don't know theta prime. We do know theta is pi over 4. The secant of pi over 4 would be the reciprocal of cosine. Cosine pi over 4 is square root of 2 over 2. You flip that over and you get something like, we're going to square it. It's 2 over the square root of 2 squared. Square root of, I got to pause. Okay, forgive me. I've got 3 kids to get to bed. My brain was not working here, but yes, I was correct. So the cosine of pi over 4 is the square root of 2 over 2. The reciprocal of that is 2 over the square root of 2, which is the square root of 2. And when you square it, this thing works out to be 2. Whew. We already know that x prime is 264 over 132, which is also 2. And all that works out to the fact that theta prime is 1 radian per second. Okay. So other than the fact that I'm getting too old for this, we've arrived at the value for theta prime, right? How fast was the angle changing? A half second later. A half second later it was changing at a rate of 1 radian per second. Well, hopefully that helped you work through the solution to number 32. We'll come back and try some other related rates problems. Maybe the videos will even be better when I get around to it. Good luck with everything you're working on.